All right, so we're going to look at the pole vaulter question here. Okay, so we have a pole vaulter whose mass is 56 kilograms trying to convert kinetic energy of their approach into height. What's the maximum height they can expect to attain if her approach speed is 8 meters per second? All right, on the ground, she has what kind of energy? Kinetic. Okay, she's on the ground still, so she has only kinetic energy. Okay, when we're looking at the final, okay, she's going over the bar. She's at her maximum height. We're going to assume she's thrown like perfectly vertically up in the air. So at her maximum height, her velocity would be 0. So all of her energy is then potential. All right, so I'm still going to say that my initial mechanical equals my final mechanical, but I'm going to simplify it to say my initial mechanical energy is all kinetic, and my final mechanical energy is all potential. Right? The other two values are 0. Initial potential is 0 because she's on the ground. Final kinetic is 0 because her velocity is 0.
But her center of mass is 0.85.
Okay, sorry. No, you're right. I missed that part because I was looking at only the first part. Okay, so initially she does have some potential energy. Okay. So EP initial plus EK initial. Good eye. Okay. So now we're going to move into this. So we've got M times G times H initial plus 1/2 MV initial squared equals M times G times H final, because she would have to get her center of mass over the bar. Okay? All right. Since I'm looking for her maximum height and not a form of energy, what can I get rid of? The mass. Okay? If they asked me what's her final potential energy, I would have to leave mass in there. But in this case, because I'm looking for either a height or a speed, those are only dependent on the acceleration due to gravity, which affects all masses equally. Okay? So I can take it out. I want to find HF, so what do I have to do with G? Divide it over. All right, that's going to get me HF. So 9.81 times 0.850 plus 1/2 times 8 squared, her initial speed, divided by 9.81 should give me the final height, okay, of the pole vaulter. Okay, so 9.81 times 0.85 plus 0.5 times 8 squared divided by 9.81. Okay, 4.11 meters. That is impressive. Okay, that is like world record territory for a pole vaulter. Okay, 4.11 meters is really, really, okay, it's like almost 14 feet.
How big is the pole?
The pole is about the size of that javelin, maybe a little bit wider, and made of fiberglass. That's it. That's why you don't see like any really big pole vaulters. They're usually quite lean. No, in fact, a lot of them are actually fairly tall. But hey, if you ever look at a pole vault, you watch pole vault on TV sometime, they're jacked. Okay, pole vaulters are absolutely super lean, and they're all shoulders and core. Okay, because so much of converting your energy is all in your arms, shoulders, and core. Getting yourself inverted to get over the bar. Okay, it's all just like being a gymnast would almost be an advantage. Oh, the pole's way taller than you. A person who would get over a 4.1 meter thing would need at least a 3.5 meter pole. I said thick, as thick as that. As thick as that. But like that, there's probably 4 meter long poles special built for these kind of pole vaulters. Okay? In high school pole vault, we have like 2.5 and maybe a 3 meter pole. Okay? In high school, it's like glorified high jump with a stick. Okay? In the Olympics, they can actually bend the pole, and that's when it gets exciting. All right, everyone follow what we did on that one. All right, so do all of these pretty much work the same? Yeah, that's the good news. Is there's really nothing new here, okay, from what you learned in Science 10. Conservation of energy is still conservation of energy. Right? Work energy theorem is something that changed significantly in terms of, we go into a lot more depth, but this is pretty much the same as it was before. All right, so I'm going to put the worksheet on conservation of energy up. I want you working on that today so we can go through any ones that give us trouble. So we're ready to look at the lab on Monday, okay, where we'll be applying all of this stuff to a real world situation.
This is on the online.
Yeah, it's on the dynamics worksheet booklet, and it's on the bottom of page 6 and the top of page 7. Okay, so let's get to work on those questions, guys. Okay, so on number 3, okay, I've got a heavy object that's dropped from the top of a building. All right, so we know these are all questions that are law of conservation of energy questions. If something is dropped, how much kinetic energy does it have? None. It's dropped. Its initial speed is 0. All right, so I know that initially this thing only has potential energy. Right? The other point it's asking about is on the ground. Well, on the ground, it would only have kinetic energy because it has a height of 0 when it's hitting the ground. All right, so this is what we've got. My initial mechanical energy is all potential. My final mechanical energy is all kinetic. And I'm looking for the height from which it was dropped. Okay, so if I want to get height by itself, I divide both sides by mg. The m's cancel. And I solve. Okay, so initial height will be 0.5 times 37 squared divided by 9.81. When I do that, I should get 69.8. That's a good number. 69.8?
Yeah.
Okay. All right. Any other ones there besides number 6? Okay, so I'm just going to give people a few more minutes to kind of get to number 6, and then I'll walk through that one as well. Okay, so let's quickly have a look at number 4 here. So we have a heavy object that's thrown vertically downward. So it's not dropped. Somebody threw it. Okay? If they threw it, it not only had potential energy at the beginning, but it also had kinetic energy at the beginning. So, okay, it's still an EI equals EF type of question, right? But initially, we have potential energy and kinetic energy. Okay? At the end, when it hits the ground, we only have kinetic energy. Okay? We can cancel the masses off, and we're looking for VF. So we would divide both sides by 1/2, and then square root. The thing we have to recognize is that there is initial kinetic energy because the object was thrown. Okay? So we have 9.81 times 130, the height of the building, plus the kinetic energy from it being thrown, so 1/2 times 11 squared, then divided by 1/2, okay, and that'll give us our 52 meters per second when it hits the ground. Okay, we can't forget there was kinetic energy at the beginning of that question. All right, now people were asking about number 6. Okay, and I threw number 6 in there for this reason. I wanted to remind you that work energy theorem goes along with the law of conservation of energy. If I do work on a system, where does that energy go? Into the system. Okay, so this is a bow and arrow system that we're talking about. If I draw back the bow using a force, okay, over a distance, what have I done? Work. Okay, when I release that bow, the work I've done will be transferred from the bow to the arrow. Okay, and it will become what kind of energy? Kinetic. All right, so there's pieces of information in this question that are meaningless. This, meaningless. Okay, it doesn't matter how far away the target is. If this is a perfect physical world, the arrow will continue to travel at the same speed it was before. Okay, so what we have is, that work is going to represent the kinetic energy, or the change in kinetic energy of the arrow. It's going to change from 0 to however much work I did. So I'm going to go force times distance equals 1/2 mvf squared. Okay, I have the force, 12 newtons. Okay, I have the distance, 0.3 meters. Okay, and I know that the mass of the arrow is 0.45 kilograms. That'll get me VF. Okay, so when I plug in my numbers, 12 newtons times 0.3 meters, okay, divided by 1/2 times 0.45, which is like an incredibly heavy arrow. No arrow is 450 grams. That's more than the carts that we use for labs. We That's ridiculous. I don't know why I picked that number. Okay, that's what happens when you pick numbers out of it. Okay, so when we do that, we should get that the speed when it reaches the target is 4 meters per second because its kinetic energy is not going to change along the way. Okay, so we still have some time here, but reminder that coming up next week, okay, on Monday, I think it's Monday, I have the lab plan, Monday or Tuesday. I'm also going to do a unit exam review, either Monday or Tuesday, okay, and then teach you about power on Wednesday. Okay, power is the last thing. There's really no math to do with power. You just have to understand what power is. Okay, and then your test on Thursday.
So we're gonna get a test review, right?
Just so.
Sorry, that wasn't the same.
I know. Okay, your review package was put on Google Classroom earlier. Okay, so it's already on there. Just go back in the stream and the review package is there. You can have a look at that over the weekend, but I'll do the thing next week, Monday or Tuesday. Okay, now, there are still a couple of questions that we haven't done on this worksheet. Okay, and I would like you guys to try them because we didn't get fully into these work energy theorem questions here. Okay, like 7 through 10, right? From the energy worksheet, we didn't get to those before, so I'd like you working on those here for the remainder of class. Okay. All right, never mind. We'll look at this one. We'll look at this one another day. But there's two ways to do it. They're both pretty short.
Wait, ready?